Welcome, everyone, to this edition of the Samsara AI and Data Speaker Series. Thanks for attending and for supporting this program as we develop it with interesting speakers from academia and industry on a variety of topics related to AI, data, and IoT. And today, we're really excited to welcome Professor John Shen from Carnegie Mellon University, who's going to present on neuromorphic computing, which combines hardware and AI. To say a brief background on John, he has a really long and storied career, which started, back in the 90s when John was a full tenured professor at CMU, where he advised, numerous students, published well over 100 books and papers. And then in the year 2000, he actually transitioned to Intel, where he was the director of the Microarchitecture Research Lab, pursuing aggressive instruction and thread level parallelism architectures for IA32 and 64. And he was at Intel for several years. Then on to In 2006, John became the founding director of Nokia Research in North America, and he was also a Nokia fellow at the time. And there he oversaw numerous teams researching a wide variety of topics in mobile internet and mobile computing. And then after a long session at Nokia, making significant impact both in research and industry, John returned to Carnegie Mellon's Silicon Valley campus, where he continues to research and advise students. And so again, today, John is going to talk about ongoing research in his group at the Neuromorphic Computer Architecture Lab at CMU. And a very exciting forward-looking research that's looking to leverage the best of biological principles and silicon technology to design highly energy efficient processors for diverse sensory processing and AI applications and other kinds of applications. So you can see there's an interesting connection to some of the work we do at Samsara as well. And so with that, I'll turn it over to you, John. And then just one more note for the audience. We're going to have Q&A at the end of the session. So if you can just hold your questions until after John is presented, we'll get to it at the end. Thanks. Over to you, John.
So neuromorphic sensory processing unit. So I head up this small team at Carnegie Mellon, and I'll explain a little bit of what I mean by brain emulating and silicon optimized as we go through the slides. So here's the quick outline for my talk today. Why? Why do we want to revisit the neuromorphic? By the way, neuromorphic is not new. It's been around for a while. The last major effort was by Carver Mead and a bunch of his PhDs at Caltech in the late 80s. And then I'll go into sort of a more lengthy section on our approach on neuromorphic. We've been at this for almost 5 years, and then I'll share a little bit about our current results and then where we're headed. And finally, I'll end with a few slides on where I see the whole computing landscape goes. And hopefully that will connect with you guys at Samsara and also the direction, the application direction that we're trying to target our research. So let's start with motivation. This thing came out about 2018 from OpenAI. And I'm going to be using their figure to do a lot of my own annotation on top of it. So they basically plot, and on the vertical axis is the log scale here, amount of compute that is required to train these new AI models. And as you can see, there was 2 periods, what they call the first era until 2012. And then there's this transition at 2012 into this, they call it the modern era. And you can see that the trend line has become much steeper. Okay, so let me see if I can. So let's focus on this modern era. And so the next slide is going to be zooming in on 2012 and beyond. So you see here, this is that modern period from 2012 until 2019. Well, this came out in 2018, and they have updated this more recently. And this is the vertical axis is the amount of compute, and this is in units of petaflops per second day, meaning 10 to the 15 operation per second, and run that for a whole day. And you can see this trend line here basically is shooting up at the rate of doubling every 3.4 months, or 10x per year. And then those of you who are more into hardware know that Moore's law at best is doubling every 24 months. So 7x slower. And so what that means is that this gap between what hardware can provide versus what these AI trainings are demanding is widening at the rate of 8x per year or 500x per 3 years. And the way that we've been addressing that is by starting in 2012 using GPUs and then 10 times the GPUs every 2 years. That's how we've been doing it. And this trend has continued. And so when I read this article, I was saying, interesting. Other people, and by the way, OpenAI is not the only one that has shown this chart. This has been done by multiple people. But in the OpenAI article, I was saying, okay, what are they going to do? And then when you read towards the end, they basically said that we expect that this trend can be continued. They seem to have this kind of a blind trust in the chip, industry to continue to provide. And the question is that trend really sustainable? Well, there are others that are not so optimistic. And this is the paper that came out in 2020 from MIT and IBM. And they basically concluded that this trend, this gap that's increasing, is not sustainable. Not only technically not sustainable, but economically not sustainable, and definitely environmentally unsustainable. And just to put out a disclaimer up front, we are in this camp. We are in this camp. And so the question is that, how do you address this widening gap? And why is the amount of compute skyrocketing at such a rate? Well, I don't know if you ever heard of this, but this guy is Hans Moravec. He's another professor at CMU. He's been doing autonomous vehicles from 40 some years ago. And he has retired, but he still shows up on campus. Well, he wrote this book in the late 80s called Mind Children, talking about AI. And he made this observation that has now come to be known as, referred to as the Moravec paradox. And what Hans did in this book was that he said, hey, sensory information processing is extremely easy for human brains, but extremely hard for modern computers. And when he said modern computer, he's referring to, the modern digital computer that started in the late 50s, with Alan Turing, John von Neumann, Eckhart Mauchly, right? So this is the kind of computer we've been building for the last 70 plus years. And he says, on the other hand, symbolic information processing is comparably hard for brain, but extremely easy for modern computers. So basically, this quote here says, Moravec's paradox states that it is easy to train computers to do things that humans find hard, like mathematics, logic, but it's hard to train them to do things humans find easy, like walking, image recognition, speech, and so forth. So coming back to the Moravec paradox, the question then arises saying that, could it be that the modern digital computer, essentially the Turing von Neumann machines, are not good at doing what humans do really well? And this goes back to saying, 70, 80 years ago, when they started building digital computers, what were they trying to do? Were they trying to build machines to do what we do really well? Or were they trying to build machines to do what we don't do well? And most people probably conclude it's the latter, right? How many of us can do a 4 decimal digit multiply in our head without using paper and pencil? Or can you do just a simple, floating point multiply of 2 numbers, right? So the question is saying, well, okay, so maybe based on Moore's paradox is that now we're trying to get the modern digital computers to do human-like perception, cognition? Could there be a mismatch that's causing this widening gap, the amount of compute needed? And so one approach is to let's go back and look at humans versus machines, right? 2011, there was this interesting competition between Ken Jennings and IBM Watson playing Jeopardy. Eventually, Watson beat Ken Jennings, but Ken Jennings was quite competitive. But let's look at this here. Here we have actually an example of human competing with silicon. And you notice that the IBM Watson is 7 orders of magnitude faster than Ken Jennings' brain. Human brains operate at 100 hertz. But on the other hand, Ken Jennings' brain is tiny compared to IBM Watson that took up an sort of entire warehouse. And it is burning 4 orders of magnitude less power. Interesting. So then if we compare biology versus silicon, we can make this observation, right? That there are certain things that silicon is great at, and that's shown in blue here, meaning it's at least 6 orders of magnitude faster and 3 orders of magnitude denser if you look at a transistor versus a neuron. And then on the other hand, biology is 3 to 6 orders of magnitude more energy efficient. 20 watts versus 200 kilowatts. And so the question is, looking at both, you can see that there are advantages to both. Can we, by the way, silicon also is highly reliable. Human brains are not very reliable. But biology has phenomenal fan-outs. The ratio between synapses and neurons is like 1,000 to 10,000, whereas a logic gate is limited by fan-outs of 3 to 4. So the question is, can we leverage the best of biology, combine it with the best of silicon? And is it possible to create something, the third option, that takes advantage of the strength of both and potentially be able to be better than both? So that's kind of the pompous ambition. And so let's, any questions so far?
I think we're good. We'll probably save most of the questions at the end. Some people are probably
cool.
transcribing them.
So let me tell you what we have done in the last 5 years. First, this is a very important slide. This captures the overall neuromorphic research strategy we have. Basically, we want to be informed by neuroscience and be able to emulate brain faithfully, meaning that we want to not only mimic the behavior of the brain or the functionality, but also its architecture, its organization, how it's built. And our research relies heavily on this book just came out in late 21 by Jeff Hawkins. It's called 1,000 Brain Theory. And this is sort of, so he's also the founder of Numenta, and they do a lot of research on neuroscience. This book came out based on their view of how the neocortex actually operates. And they have this notion of cortical columns and reference frame, which I'll get to in the next slide. The other thing is that we only want to be diligent in adhering to biological plausibility when it is truly beneficial. There are certain attributes of biology that may be due to the weakness of the kind of circuit that you build using, chemical reactions. So, and then we want to also then at the same time be able to leverage modern silicon. Since Carl Ramin and his students took this neuromorphic approach in the late 80s, it's been 35 plus years of advancement, both in neuroscience research as well as the silicon technology due to Moore's law. So we want to be able to do both. We want to sort of learn from the brain, but we want to leverage the best of silicon. And this is kind of like the full stack that our research team is focusing on. We want to span the whole thing. We want to start from the top with edge native online sensory processing, and then take it all the way down using the cortical column computing system model that we derived from Hawkins' book. And then there's another sort of giant that we are building our research on, which is Jim Smith, who retired from University of Wisconsin in 2007 and moved to Montana, spent most of his time fly fishing and backpacking, and the rest of the time working on Neuromorphic. So he basically embraced sort of the same approach and spent the last 15, 16 years trying to reverse architect the brain and using that reverse architecting to see if we can build it. And then we are essentially taking his overall microarchitecture and trying to see if we can actually implement it. And our assumption is that we want to use existing off-the-shelf digital CMOS and all the tools and to see, can we do it? And the reason is because our interest is, having spent 15 years in the industry, I'm very much interested in having research that impacts the mass market computing in short amount of time. So this slide kind of gives you the big picture. And let me just touch on Jeff Hawkins and Jim Smith's work. One slide doesn't do justice, but, so this book came out. It's a very interesting thing. It's a new theory of intelligence. And basically what Hawkins says is that the neocortex is made up of these things called cortical columns, many of them. Humans have 150,000 of these cortical columns, and every cortical column is built from, potentially up to hundreds of mini columns. And so these are all terminologies for neuroscience. And the important thing is that every cortical column is capable of learning anything, but not everything. And that if you look at all the mammals, the higher level intelligent mammals are more intelligent, not because they have different cortical columns, but they just have more. So what that means is that even one or two cortical columns can perform intelligent function, right? And then each cortical column has inside it the thing that he calls reference frames, consisting of what neuroscience calls place cells and grid cells. And this is the map that the cortical column builds as it processes its sensory information, looking at the environment and construct a organized structure storage of previously observed, learned information. And what's cool about this is that it matches computing or parallel computing really nicely, in the sense that we don't need to replicate human with 150,000 cortical columns. Can we get just one cortical column to do something compelling, useful for us? And so this is sort of a, kind of and there's a lot more to it. You should pick up a book. It's a very easy to read and fascinating. So we bought into this as our overall computing models. And by the way, the cortical columns are specialized somewhat. They all basically share the same architecture. The only difference is that each cortical column is fed by a particular sensory modality. So you can have multiple columns fed by different sensory modalities, but once those sensory modality signal gets converted to spikes, the rest of the cortical column operates pretty much the same way. And then the other thing is that these cortical columns, fed by different sensory modalities, they do voting to converge on a consensus view of the world. So that doesn't get, completely chaotic. And then here's Jim Smith's work on what he calls space-time computing with temporal neural networks. And basically, if you look at this taxonomy of neural networks, you can see that the rest of the world is on towards the left, and Jim is focusing on the right, and mainly because it is the most neuromorphic, meaning mostly like biology. And so, first of all, the brain uses spikes communicating between neurons to do its processing. And also, the encoding of information is done temporally, meaning it is not storing multi-bit binary values. It uses a single wire to transmit spikes. And the value is carried in the relative delays between spikes. So what Jim's saying is that, in digital logic design, we try to remove the effects of timing, but the brain uses timing. It's only a single bit wire that's carrying a spike, and the value is in the relative delay. And I love what Jim Smith said. He goes, our brain uses time as a resource to represent values because time is always there and it's free, causes no gates, no transistor. It's just always there. And human brain is using that. And so the question is that, can we build it? And then also the learning algorithm is local, called STDP, spike time dependent plasticity, meaning it is using the relative time of spikes coming into a neuron and then exiting a neuron to determine whether you should strengthen the synaptic value or not. And it's all done locally. There's no global backpop, to do stochastic gradient descent, and very complex. So our brain doesn't really do a lot of the things that all these artificial neural networks does. So this is kind of a big picture of what our whole research team is trying to do. As I said, we want to start from application, go all the way down to hardware. And we're, the rest of the world is on the left-hand side here. And it ultimately goes from application architecture down to hardware, which mainly is a massive arrays of MAC processing unit, multiply accumulate units, right? It's basically doing matrix multiply. And the question is that if we take the neuromorphic approach on the right-hand side here, can we produce something using same current off-the-shelf digital CMOS? A new chip that can give you potentially 3 orders of magnitude improvement on the hardware metric, PPA, performance, power, die area. And so along with this research, we are also trying to build this whole tool chain in those 2 yellow rectangles of starting out with, say, PyTorch, and then be able to go all the way down and spit out a chiplet, and that you can then integrate into your system. So this is kind of our whole approach, and this section I'm going to kind of zip through. We have published a bunch of papers that you can look up. Go to our lab's website. So what we decided to do is we came out with this architecture, I guess you could call it, with these 4 layers of abstraction, trying to leverage the best of what's on the left, silicon, and biology on the right, to come up with something in the middle here. And then we have these similar kinds of layers of abstraction. Start out from the low-level building blocks of neurons, dendrites, synapses, and the local learning rule, STDP. WTA is winner take all. Your neurons not only are some are excited, that there's excitatory neurons. There's also inhibitory neurons, and the inhibitory neurons is what's keeping your brain from going into seizure, right? It's damping. It's the damping for the winner take all is a voting, selecting to achieve lateral inhibition. And then from there, we build what's called mini columns and then macro columns. So, and we have started this process going from bottom up and up through sort of level 2 there, mainly like, can we produce a new kind of processing units for AI hardware? And this, I know you guys not necessarily a chip company, but so I'll just run through this. So let's start at the lowest level, right? A neuron. This is a classic model of how a neuron operates. You see the neuron body there with a summation sign, and then you have these dendrite that's feeding into a neuron. And every dendrite is gated by a synaptic weight. And so when the input spike comes in from the left, as it hits that weighted value, it produces this thing called a response function, and you can see that it's shifted in time because the timing of the incoming spikes. The amplitude is also determined by the value of the synaptic weights. And then the neuron body performs the summation. And when that body potential gets above a certain threshold, then it spikes. It sends out another spikes on the output. So dendrites are inputs to the neuron, axons are output from the neuron. So now we have this model on the right is basically our neuron model adding in this STDP. And notice that the feedback is basically from the input to the output of the neuron, and then updating each of the synaptic weights accordingly, either incremented or decremented. And basically, this is based on what's known as the Hebbian learning model, meaning that if you have an incoming spike from a presynaptic neuron hitting a synapse and then resulted in the postsynaptic neuron firing, that means that those two neurons are correlated. And so therefore you increment the weight to give it more strength. So this is kind of a model for a neuron. And then from there, the next level up is bundling multiple neurons into a column. And so now you have this multi-neuron column. Let's say in this case, you have Q number of neurons, all share the same P number of inputs. And that creates this synaptic crossbar or synaptic array with P times Q number of synapses. And those synapses carries weights that can be incremented or decremented. Here you're seeing an illustration of, say, assuming that, and most neuroscience have come to realize that the synaptic weight precision only needs to be at best 3 bits, right? Meaning that all you need to do is be able to difference between, less than 10 different weight values. So the question is that, can we implement this using digital CMOS? Okay, here's also illustrating the winner-take-all, the lateral inhibition. You notice that these values comes into the lateral inhibition, and the earliest neuron that fires gets picked, and the rest gets erased. And then that spike goes on to trigger other things. So the way you can look at this is that this mini column is a foundational unit for building TNNs, temporal neural networks. And what it's doing is saying that I'm looking at these P input signals, and I have these Q neurons, and each neuron is trying to capture a particular pattern. on the input side. And as it learns, it will then inhibit the other ones, and it gets better and better at learning that pattern. So this column here, for example, allows you to have a mini column that is trying to identify 8 different patterns on the input. So long story short, we have been able to implement this and in digital CMOS. So this is our foundational building unit with columns. You can see here on the lower left, those are the learning rules, STDP, as well as RSTDP, reward-based or reinforcement STDP. So then, you can build these single column TNNs, and they can perform very useful functions as is, or you can go and stack multiple mini columns, form a layer with multi-columns, and then cascading multiple of those layers to create multi-layer TNNs. And so we have created a design environment that allows you to essentially parameterize all of these designs. And so just to show you, okay, what can you really do? Well, we use the most well-known MNIST, right? This is the decimal digit recognition. And what you see on the right-hand side there is from David Burke's book from 2017, 18. And those points are essentially all the MNIST performance. On the vertical axis is the power consumption. Horizontal is the prediction error. And so you can see that there seems to be some kind of a boundary there of how well you can perform in terms of accuracy and how much power. So what we did was that we took a neural network that's the closest to ours from Simon Thorpe's group that came out in 2019. And this is this example right here. It's a 3-layer spiking neural networks. And you can see that on the right, this baseline network sits right on the edge. So meaning that it's as good as all the other examples there. And this network looks very, it's the most similar, but it was only able to achieve 97% accuracy, and it requires over 36 million parameters. And then you see the 3-layer network, the sizes of that. Using 7-nanometer PDK, it was consuming about 246 milliwatts. And then we start building our TNN from a small one, 2-layer, to a medium one, 3 layers, finally to a 4-layer. And these are plotted right here. And you can see that we're on a different line. Remember, the vertical axis is log scale. And our best, the large one, is a 4-layer TNN, achieving 99%, requiring only 3 million, not 36 million parameters. And in 7-nanometer, burning 21 milliwatt. So this is clearly a significant advancement. And if you compare it to sort of the GPUs at the top, those are the triangles at the top, we do see this potential for multiple orders of magnitude reduction on power. So this shows promise. Now, of course, we're hardware people, so we want to do further optimization. And so along the silicon optimized. So far, we have basically used the standard, design tool chains to produce these results here. And, the normal standard cell library. So we say, hey, what if we add in 9 custom macros into the cell library and use these? And because these macro cells are built based on what we need. And so you can see that we have 3 of these macro cells targeting targeting the STDP learning, and 2, for being able to store and read out these synaptic weights, and then 4 others macro cells. And so we then insert our new custom macros into the cell library, and then allow the synthesis tools to use our macros instead of just the standard one. And we were able to achieve, significant improvement. And that's the, and remember, it doesn't look like much improvement, but this is log scale. So again, you can see this multi orders of magnitude improvement on power running MNIS. And just to highlight sort of the best we're able to do, 17, 18 milliwatts, 26 millimeters square in terms of die area. We took it all the way through even physical design, place, and route. And then if you go to something more like single column TNNs, it could perform time series signal clustering. Here's just some example from the UC Riverside benchmark, said that tiny, and you're talking about 10 microwatts and 0.01 millimeters square. These tiny chiplets can perform useful functions. And then we also tested out running MNIS. Our TNNs for MNIS is capable of doing online incremental continuous learning. And you can see this is an example showing we train it without using the number 9. And then when we in test, we start feeding a 9. You can see it only took 500 cycles to learn. So, and just really quickly, this is not in the slide set that I had sent to you guys, but we're also looking at, instead of using flip-flops to implement this synaptic array, can we use SRAM bit cells? And the answer is yes. And so here's one of our paper just came out this year on using SRAM base, and then do all of our compute in terms of, weight readout, weight update for implementing our STDP learning rules, and be able to do this whole thing using SRAM cells instead of flip-flops. We're also looking at, in terms of implementing the reference frame, where we want to keep this table of previous things observed, previous things learned. And we believe using content addressable memory is the way to go for building reference cells. So we have a paper coming out later this year on CAM-based. And this is just kind of highlights what we're also trying to do. We're trying to say, hey, can we take a lot of the current models like transformers, LLMs, generative AI, and can we then, map it over to our kinds of hardware and be able to achieve, again, the goal is 3 orders of magnitude improvements on PPA. So that's kind of sort of a quick summary of our research, and I'll just take 5 more minutes to sort of wrap up and to, hopefully connect to you guys in terms of what we're trying to do. So this is my view of the computing world, right? Computing basically occurs in the cloud, or on the other side, IoT, and in the middle is mobile. And this is just my own, personal opinion here in terms of what I see as the current dominant trends in computing landscape. And I'll sort of step through each of these quickly, starting with the cloud. What we're seeing in the cloud is that this has become a highly competitive cloud infrastructure and providing cloud services. And the dominant workload now that's being run are these large, huge LLM, generative AI, and all of these cloud companies that are not only clouds, but they have built their hardware. And when I say hardware, it's not just boxes, but chip teams. And, including these companies, Amazon, Google, Microsoft, all have chip design teams trying to build their own accelerator for their cloud infrastructure. And so, and then there are a whole bunch of other companies involved. The bottom there, the key question now is that currently NVIDIA dominates in the cloud, running all of these AI workloads using their GPUs. All these other cloud companies are developing their own accelerators, AI accelerator, Google's tensor processing units, neural processing units, and so forth. And so that they can add differentiation to their cloud service. And then there's like always the question, which CPU. And in the middle area there, the mobile, are the edge and mobile device. There seems to be a convergence of computing and communication, meaning that a lot of your cellular infrastructure is gaining a lot of AI capability and is providing not just connectivity, but services for the mobile users. And because it's out on the edge, could be mobile, there's needs for improvement on energy efficiency. So here you have, I included both like cellular, technology provider as well as mobile device, providers. And what's going to happen with 6G? Very interesting. But I want to get to this last one, probably of the greatest relevance. In terms of IoT, this area is the global distributed AI sensory network, the necessity for online, on-device, continuous learning. And I personally believe that just like the low-end laptops disrupted the high-end desktops, as well as the supposedly low-end mobile phones has completely disrupted the higher-end laptops. So there's this kind of disruptive AI inversion. And normally you would view that IoT compute is sort of on the low end, out there on the edge, but I believe there could be a potential inversion disruption as well. The technology developed for the edge sensory capability is going to ripple back in all the way potentially into the cloud infrastructure because of its energy efficiency. So this is my last slide in terms of where we're targeting our research is can we produce a whole new types of sensory processing units for mobile as well as for IoT.
Thank you so much, John. This super fascinating area. Not many of us get time to hear more about, so it's really useful.